And so to kind of summarize the topic today, it's very broadly speaking gravitational waves, but we'll try to focus a little bit more on binary black holes. So one of the things that many people here have probably heard about is that gravitational waves were detected in 2015. So it's a relatively new area of research. And since then, the field of gravitational waves has grown into a very big observational field where we have used gravitational waves to study binary black holes, extreme gravity, binary neutron stars, and things like we've constrained general relativity at very high accuracy, and even measured the expansion of the universe with all with gravitational waves. And so since I know that many people here are not too familiar with what gravitational waves are, we'll just focus on some of the basics. You don't need to have too much GR knowledge for this, but what we'll mainly focus on is, what are gravitational waves and what actually emits them? How does that process actually happen? And so what you can see here is a video, is the simulation of the first detected gravitational wave, and it pretty much summarizes everything that is going to be in this lecture. So basically, everything that we'll talk about is within this simulation. What you can see here is two binary black holes that are orbiting each other. They're emitting gravitational waves, where you can see this gravitational wave curve towards the bottom of the screen. And in the canvas, there is the representation of the space-time curvature around those two black holes. And what you can see is that the two black holes are emitting gravitational waves. So if you look very far away, and because of that, they're losing orbital energy, getting closer, and the gravitational wave and orbital frequency increases. And what happens in a bit when the movie freezes is that the two black holes merge. There's this extreme space-time curvature around the two black holes, and the two black holes merge and emit the last of the gravitational waves away in this sort of ring down process. So essentially what we want to try to understand is, how does this process actually happen? So how are these gravitational waves emitted? What do they do, and how do you detect them? And so the first bit that is usually important to try to think about is gravitational wave propagation. So independently, before going into, let's say, looking at what kind of things emit gravitational waves, what is important to understand is what do gravitational waves actually do to matter. And for those that have done a GR course, what typically is done at kind of the end of some of these introductory courses to GR is they derive the wave equation for general relativity. So I'll go very quickly to these notes to just explain the idea, those that might be interested in the GR aspects without going into the detailed derivations and so on. Basically, whenever we're talking about general relativity, we are essentially solving this equation. So the Einstein field equations. What this equation is, in essence, says is that space-time, so the g mu nu, tells matter how to move, and the matter t mu nu tells space-time how to curve. And so a little bit like with the with electrodynamics, almost everything that you do with general relativity, you can start with the Einstein field equations and derive the rest of it. So just like in electrodynamics, we have the Maxwell's equations, so we can derive a lot of interesting quantities from there. The Einstein field equations for us is basically the same as the Maxwell's equations for some of the electrodynamics people. And the usual derivation for gravitational waves goes as follows. So essentially, we start with the metric tensor, and we decompose it into a flat metric, and then some small space-time perturbation, where h mu nu is very small. So we make a small perturbation. We assume a vacuum, which means that t mu nu equals 0. And we also are free to choose the gauge for this metric. And typically what people do is they choose a gauge in which this holds. So this is the so-called Lorentz gauge. And through a bit of derivation, by basically taking all of this and inputting it into the Einstein field equation, what we find is the wave equation. And under these assumptions, when we actually study the wave equation here, what we typically find is that the gravitational waves, when they're traveling, let's say, in the z direction, where let's say this is the z direction, what happens is that the gravitational wave has components in the x and y direction. So it looks something like this, the metric tensor. And a relevant question to ask, kind of beyond the fact that there are some gravitational waves that are produced by GR whenever you make this sort of small perturbation, it seems to produce a wave equation, so some kind of waves exist in space-time. Another question to ask is, what do these waves typically do to things? So for example, here, if this gravitational wave is traveling in z direction, then what happens if it encounters something? So let's say that it encounters a ring of masses. So there are point particles in a ring like this. They're freely floating in space. What happens? And the general result that you get by analyzing this situation is that the gravitational wave basically stretches and squeezes space-time in the x and y direction. So what does that mean? It basically means that let's say that there is a plus polarized gravitational wave that travels through this ring of masses, and we are here as an observer. Then what happens to the ring of masses is that it will squeeze here in the y direction, and then it will oscillate and stretch in the other direction. So this is the so-called plus polarized gravitational wave. The cross component here just means that there is another degree of freedom that can stretch the ring of masses in the x direction. So basically stretching in the plus direction or cross direction. That's where the kind of the naming comes from. Okay, so basically the idea is that whenever a gravitational wave travels through something, it stretches and squeezes space-time in the perpendicular direction. So that's a little bit on the kind of the theory side for those that might be interested in where these things come from. and we can take a look at the actual animation of this sort of stretching of space-time. So there is a nice animation on YouTube that we can watch. So there is a ring of test masses, and there is a gravitational wave that is traveling through those test masses. And you can see what happens. So there is linear polarization. So this is the plus polarization that I was talking about. There is this sort of oscillatory motion. It stretches and squeezes space-time. But then if you have plus and cross polarization in the wave, you can also have circular polarization where this the gravitational wave is this sort of kind of circularly polarized. But essentially, you can see that what happens is that it stretches and squeezes space-time, but only in perpendicular direction. Okay, and so that is the very fundamental and basic of what happens when gravitational waves propagate and what do they do to things. So now we can have a quiz, which the question is, which direction does the gravitational wave stretch and squeeze space-time? So there is a doodling there where there's a gravitational wave that is traveling in the z direction, and it hits this ring of test masses. So the question is, which direction does the gravitational wave stretch and squeeze space-time? If the question is not so clear, feel free to just ask for clarifications. These answers are not something that we don't. It's not shown who votes for what, so we basically have only the statistics at the end.
Okay, everyone is voting for XY, where the original graph was this, and so clearly everyone is in agreement that it stretches and squeezes space-time in the XY direction. So gravitational waves are essentially stretching and squeezing space-time in the perpendicular direction. Okay, so why is this important? Why do we care about which direction the gravitational wave stretches and squeezes space-time? It kind of goes into how we can try to detect gravitational waves, and that is done by laser interferometry. So what I have prepared here is another illustrated video where there is a simplified version of LIGO, which is the detector that made the first gravitational wave detection. And the way that we try to detect gravitational waves is that we try to detect this stretching and squeezing of space-time. So we do this by laser interferometry, where we try to basically produce two laser arms and measure length displacements between the two arms. And this video essentially shows how that process happens. So you can see that there is a laser that shoots a laser through this beam splitter, and there are two mirrors. It shows the actual thing. So there's a laser that shoots through the beam splitter. It splits the beam. The beams are reversed by the mirrors, or reflected, and then the two lasers recombine at the beam splitter to form a destructive wave. So you can see that at the photodiode over there, there's nothing that can be seen. But then if the two mirrors actually move, what happens is that you can see that the photodiode sees and observes this sort of flickering at the detector. And so the basic idea, therefore, is that when we have a gravitational wave that is traveling through this apparatus, what happens is that let's say there's a gravitational wave that travels here. What happens is that it can stretch the space-time in this direction, and then after some time it squeezes it in this direction. And because of that, the two arms are going to be slightly displaced relative to each other, and what we can measure is that length displacement divided by the total displacement. So this is the so-called strain you measure. And so whenever a gravitational wave is passing by, what happens is that there will be this flickering at the detector. Now this is of course a very simplified version of what actually happens in reality. And so take it with kind of a grain of salt. There will be the actual apparatus is going to be much more complicated and sophisticated than this Michelson interferometer device here. But the basic idea holds. So we have two arms, so we measure length displacement when gravitational waves propagate through this instrument. Okay, and so with that knowledge, now that you know that we're measuring length displacements and that when gravitational waves travel through this sort of apparatus, I have another question that people can fill. This might be a little bit more difficult, which is suppose that there are two gravitational wave detectors that are identical. So what does it mean by identical? It means that the two gravitational wave detectors, just like the laser interferometry that you saw just here, they are oriented in the same way, so towards the XY plane. Here, XY plane. And there is a 45-degree angle between the x-axis and the arms. And so what is different between these two situations is that in those two scenarios, there's a gravitational wave in the first one that travels here along the x direction, and in the second scenario, it's traveling through the z direction. And so the question is, which one of these gravitational waves measures the gravitational wave better, or with larger displacement? And well, the other option, of course, is that that one of the gravitational wave detectors measures the gravitational wave and the other one doesn't. And so I'd like everyone to vote what they think based on the first question and based on kind of the illustration that you saw about this laser interferometry.
People voted. Okay. So there's a little bit more disagreement. So some people, I think that the ones that received the most votes were the blue one and the green one, where essentially the second, everyone seems to, or most people seem to agree that the second instrument observes strong displacements. But then there is disagreement as to whether or not the first one, and let me get it up here. The first instrument is measuring something, or whether it's measuring absolutely nothing. Okay. So, well, firstly, let me ask, why do people think that the second apparatus is measuring larger displacements?
Let me see.
Yep, go ahead. I think we don't have to have handouts. I think.
Okay.
Yep.
I think because for second instrument, if the polarization is X direction, then one beam will have contraction, the other beam will not have contraction, and then the interference will see decoherence. But for the first beam, because either for the plus mode or the cross mode, either case it will not measure the length contraction. I mean, there will be less contraction, but the two beams will have the same length contraction and cancel each other. There will be no decoherence in that case.
All right. Okay. That's a good answer. And so let me see if I got the answer correctly. So to understand that I got what you mean correctly, that essentially in this case there is you know, let's say strong. Well, there's going to be contraction along the perpendicular direction, and this arm and this arm doesn't change when the gravitational wave passes by. The two arms don't change at the same rate. Is that what you mean?
Yeah. I'm thinking if the plus mode, then I think they change at the same rate. If the cross mode, they don't. Yeah,
exactly. So basically, that what you're saying is that let's say that this is the plus mode, and then this one is the cross mode. Then the cross mode would give you a very strong length displacement. So one of the arms would be displaced or squeezed, and one of the arms would be stretched. Is that what you mean?
Yeah, basically.
Yeah. Okay. Do people agree?
Okay. I think I would tend to agree as well. I think this explanation is good, and I find it satisfactory. So then the question then is this first one. So what actually happens when the gravitational wave is traveling along x-axis? So if I understood correctly, and maybe I can summarize it if I got the argument correctly, that the idea is that there will still be, again, stretching of space-time, so there could be some stretching in, let's say, this direction and this direction, but they are stretching both arms at the same rate, and therefore you don't see the plus one. Is that what you mean? Yes. Yep. And then for the cross one here, they would again stretch the arms to some degree, but they would be stretched at the same rate, and so therefore the displacement is zero. Is that what you mean? Yes. Okay. Do people agree?
Okay. I found the explanation convincing. I would, if people think there are other better answers, feel free to speak up. But I think I would accept that as a reasonable answer, that there is no displacement in the first detector. Okay, so let's then move on. So we've looked a little bit at gravitational wave propagation. So you understand that they stretch and squeeze space-time in perpendicular direction, and we can measure it with these laser interferometers. But another question that we haven't really answered is how are gravitational waves generated? So to that end, we will take a quick look at the lecture notes. So when we solve for the gravitational wave propagation, what we could assume is that there's a flat space-time around everything, and that the T mu nu, so the source term, is 0. But in the case that we have a binary black hole, so something like this. In the case that we have a binary black hole, then we can no longer make that assumption. We again start from the Einstein field equations. And it turns out that in the Lorentz gauge, where this one is 0, the Einstein field equations basically reduce to the following. Sorry. Where this looks like the previous wave equation, but then we have a source term and some high order perturbative corrections. So again, if you remember, h was much smaller than 1. And it turns out that this is the exact field equation in this gauge. And what people can do is they can essentially solve this equation. This is, by the way, trace reversed notation. So they can solve this and get the following solution. Okay, this doesn't actually say much to most people, but what I want to say is that basically everything here that is happening is just manipulating the Einstein field equations. Nothing kind of particularly impressive is needed. But if you make the assumption here that for this binary black hole, the characteristic radius of the source R is much smaller than the gravitational wavelength, which is smaller than the distance to the source, where this would be R. You can solve the wave equation to essentially find that this is the same as 4g c squared T mu nu T minus R per C where this is the same as approximately the same as 4G C4R. And this sort of momentum tensor here. And it turns out that you can actually produce a lot of predictions based on the Newtonian formula, where essentially in the Newtonian limit, this tensor Iij is essentially an integral over the mass density multiplied by the spatial coordinates. So you form this sort of tensor. And it turns out that for this sort of binary system where you have a two masses that are orbiting each other, there is a solution for this h mu nu, which is roughly proportional to, and I'll skip some of the derivation here. Which is proportional to this quantity, where the amplitude here is the radius and the orbital angular momentum and the distance to the source. And what you can see is that the frequency at which the gravitational wave oscillates here is determined again also by the orbital angular momentum. So the gravitational wave frequency from the system is twice the orbital frequency, which I think is quite interesting. And so with this equation, I'd like people to answer the next question. Which is, supposing that we have a binary orbit, which of the following is true? So this is just to explain a little bit more. This here is the gravitational wave amplitude. Omega is the angular frequency of the orbit, d distance, r is the separation, and so essentially what you have is a binary black hole that is, there are two masses that are equal, m, and they're orbiting each other. There's someone who is observing the gravitational waves, and the emission is determined in the Newtonian limit. So this is a very approximate formula by that equation over there. Which basically sets the frequency of the gravitational wave. It sets the amplitude of the gravitational wave, and basically what the person over there observes. Now, this is what is worth mentioning is also, of course, is that this h is an amplitude, whereas in reality the gravitational wave is described by a tensor and not a single scalar equation. And there are going to be more than, or there is possibly more than one answer that is that could be correct. And then after this this question, we can probably wrap things up, and then in the next lecture we'll have the rest of the slides. Okay, so there are 13 people that think that the gravitational wave amplitude is smaller at larger distances. There is nobody that thinks that the orbit is always time invariant. And there is some people that believe larger mass implies lower frequency. Okay, so would anyone like to volunteer to explain let's say the answer to why the binary orbit is not time invariant? Why they think that it's not time invariant?
Well, you shoot out waves, and presumably that carries energy and energy and does momentum away from your system. So then you lose the, I guess, angular momentum in this case, and the thing has to collapse. Right.
Yeah, exactly. And in that case, it's basically follows just from energy conservation that since energy is being emitted away, it has to come from the orbit. And yeah, that it seems like everyone agrees to that as well. Yeah, thanks a lot. Okay. Then in that case, are there anyone who would like to? I mean, the gravitational wave amplitude, I think, is quite clear in the sense that from here, the distance is inversely proportional. So if you increase the distance, the wave becomes fainter, and of course, the amplitude is harder to measure. The decreasing orbital radius increases gravitational wave frequency. There's only 50% that answer to this, but if you remember Kepler's third law, you can relate the orbital angular frequency to gm per r cubed, where r is the radius of the orbit, and therefore if you decrease r, the angular frequency goes up, and here the gravitational wave frequency is twice the orbital frequency. And so basically, whenever you have smaller orbits, the frequency becomes larger. And that's something that we see with gravitational waves as well. So whenever binaries are merging, what we can see is that the gravitational wave frequency goes up, and so does also the gravitational wave amplitude. There is also some very small support for larger mass implying lower frequency. Here you can see from the mass that increasing the masses essentially increases the frequency. And so that then is incorrect then. And so it's the opposite, larger mass implying higher frequency. Okay, and so excuse me. So I think that this is probably a good point to stop for today's lecture. We'll continue at the next one for we'll continue tomorrow at, I think, Chunlong is at 4 p.m. That is the next lecture.
Yes, he said 4 p.m.
Yeah. So we'll continue and pick off kind of where we left off tomorrow at 4 p.m. and we'll look at a little bit more in detail how the binary evolves when the gravitational waves are being emitted, what kind of waves are being produced by that, how do you actually get to, let's say, the gravitational wave, like the energy carried by the gravitational waves. And by the end of the second lecture, what I'm hoping for is that we can have a complete picture of how we can get from two black holes or a binary object, how we can get from the very beginning towards the very end of the binary spiral, what kind of gravitational waves you can have from there, and what that actually tells us. So if we measure a wave from an object like that, what can we learn from it? So thank you very much for coming to the lecture. I think for the next lecture, we'll change the format a little bit. So we'll have probably still polls, but we'll kind of tune the format a little bit based on the feedback survey and other things. So thanks a lot for participating.